Hi, my name's Lawrence, and today we're just going to go over a quick introduction to differentiation. So when we're looking at differentiation, the first we need to understand is what differentiation actually is, what are we actually looking at here. We're looking at a method used to calculate the rate of change of y with respect to x. So differentiation is just trying to find this change in y with regards to how much x is changing. You'll have seen this in the past. This is just sort of when we talk about the rate of change of y with respect to x, we're just talking about the gradient of a line. How much is x changing when y changes? And differentiation is essentially just trying to find this gradient. We also sometimes say, we sort of refer to it as the derivative of the equation of the line. But most commonly, you'll see it as the gradient. What is the gradient of the line? Differentiation will find this gradient. In a more mathsy way, I guess, you'll sort of see it referred to as this sort of delta y over delta x and dy over dx. Don't be intimidated by this. All it is just another way to say the gradient delta and d here, just say change in. So all this is change in y over change in x, or change in y over change in x. They'll just sort of say delta y over delta x equals and then the gradient. Now, when we're actually trying to find the gradient of a straight line, which is something you will have done in the past, we're just sort of looking for this change in y and this change in x. So on this graph here, y equals x plus 1, this line, we're just going to look for the change in x here. So there's a change in x of 1 here. We're going to look for the change in y here, so that's just a change in y of 1. So when we put this over here, we're just going to find that this is just 1 over 1, change in y is 1, change in x is 1, and this is just equal to 1. So a relatively simple one there, just looking for change in y and change in x on this graph, something you will have done in the past. But yeah, it's relatively simple just because this gradient is going to stay constant for this straight line all the way up for every value of x, going down, going up, no matter what. The constant gradient is always going to be 1. This does become slightly more complicated when we start looking at curved lines. So when we start looking at a line, for instance, like y equals x squared, we're going to find that the gradient actually changes for each x value. So when we're sort of looking at this value of x here, so if we take a value of x on this side of the graph, we're going to find that the gradient is negative. It's got a sort of, it's going up here in x by, for instance, 1 maybe, and then it's going down on the y-axis. So it's going to have a negative gradient here. And that is not the greatest of lines there, but it's a flat line at 0, and the gradient at this sort of point here at 0 is just going to have a gradient of 0. Y is not going to change as x changes. And then here, take a look at a line here, we can find the gradient at this exact point of the curve is going to be positive. X is going up, y is going up. Now what we're doing here is basically what we did earlier. For each point of the line that each point of the curve that we're trying to find, we're taking a straight line and we're working out the gradient of that straight line. Now this straight line is called a tangent. All it is just a straight line that just touches the curve ever so slightly at one point. And at this point, the tangent is exactly in line with the gradient of the curve, and so because of that we can then work out the gradient of the straight line to work out the gradient at that exact point of the curve of y equals x squared. However, I think, as I've probably aptly shown through my quite bad tangent drawing, it's actually quite difficult to draw accurate tangents, and it can be quite time consuming, especially when you're having to do it for each new point you're trying to work out a gradient of. And so actually working out the gradient through this method can be, time consuming, it can be complicated. It's just not the best way to go about it for a curved line. So what we need to do is sort of find an algebraic version that can give us every point on the line, a formula that just gives us every point on the line, so that we can just plug in an x value and that will give us the gradient. And this can be done through chords. Now I'll sort of first show you what a chord is and why it can be used to estimate the gradient. So a chord is just a line that goes between 2 points on the curve. So for instance, if we had a chord that goes between this point here and the x value of 1, this would be a chord between a sort of x value of, like 0.4 and this x value of 1. And this chord can be used to estimate the value of the gradient. if I sort of draw a tangent here, which can be used to find an accurate version of the gradient, we can see that it's not the same as the tangent. It is just an estimate of the gradient at this point 1. It's not going to be completely accurate, but it will show an estimate of it. Now what we can see is this estimate of the gradient, as we get close to this value of 1, you can see that this line here is actually a lot closer to this tangent than this line here. What this sort of shows is that the closer the 2 points of a chord, the more accurate the gradient, so the closer it is to the tangent of that point you're trying to estimate. And so we can use this to sort of do an algebraic function here. And that's what we're going to use the chords for. So I'm just going to remove the current chords and tangents we've got on the graph to sort of tidy it up. Remove my ruler function. And what we're going to do is we're going to sort of use an algebraic chord to work out a general function for the gradient of the graph, for the curve. Sorry. And so this can be done at any point, but I'm just going to mark it here for clarity. So if we just take this point here and we call this point x, that's our x value. Our x value is x here, and our y value for x is going to be x squared, because y is equal to x squared. And then if we take a point along the line, we're going to call this point x plus h. It is essentially h distance away from x. And our y value for x plus h, sorry, is going to be x plus h all squared. Okay, again, it's just y equals x squared. So what we're going to do is we're going to try and find the gradient of this sort of formulaic version. So we're going to find dy over dx. So this is equal to, so let's take our two y values first. So x plus h squared minus x squared. Then so that's our change in y. Then we're going to take our x values for our change in x. So x plus h minus x. And what we're going to need to do is just simplify this formula here. So first things first, we're just going to expand the brackets of x plus h squared, which I've just realised I've put the squared on the inside here, which is not where it should be. So this should be x plus h squared. Right, so we're going to expand the brackets for x plus h squared now that it's corrected. So x plus h x plus h. So we're just going to expand the brackets. So we're taking x times x is x squared. Then we're taking x times h. So call this h x. And then h times x, which is just another h x. And then we're taking h times h, which is just h squared. So what we're going to do is just plug this back into our formula over here. So I'll change colours back. We're going to put this back in. So our change in y is now x squared. And again, we can sort of mush these two hx's together to form 2hx plus h squared minus x squared. Now this is all over x plus h minus x. Now again, we can simplify this. We can see that there's an x squared and then minus x squared here, and an x and a minus x here. So we're just going to remove those. They're going to cancel each other out. So we're going to end up with 2hx plus h squared. It's all over h. Okay? So just scroll down to give myself some more space, especially with my atrocious handwriting. So we're going to look here and try and cancel out even more. We can see that we can divide through by h. So get rid of an h here, get rid of an h here, and so we're going to be left with 2x plus h. Now, as we discussed earlier, we're going to try and look for an accurate tangent here, and we discussed that chords are only giving us an estimation of the tangent. And so what we want to find is a chord that is sort of infinitely small. We're going to look for something that reaches right to the limit of h, and h tends towards this value of 0. We're going to slowly move towards 0, and when h is equal to 0, we're going to have that exact value of the gradient at the point. X is going to be infinitely small, and it's going to be exactly the same as the tangent, and this will give us the exact value of our gradient. And so I'm just going to scroll down to give myself a little bit more space even. We're going to basically make h equal to 0 here, so we're going to take dy over dx, and we're going to say that is all equal to 2x. So this here is our general formula for the gradient of y equals x squared. And what we can find is if we plug in a value of x here, we can actually find this rate of change of y with respect to x at any point. So if we put 0 when x is 0 in here, we can find that 2 times 0 is 0, and as we saw earlier, the gradient at 0 is 0. And for instance, if we put in this value of 1 that we were trying to look at earlier as well, we could put 1 in here. 2 times 1 is 1, and that would be the 2 times 1 is 1, 2 times 2 is 2, 2 times 1 is 2, and so the gradient at the x value of 1 would be 2. And this can be done with any value along this curve. This is just a general formula for the curve. Again though, this is relatively time consuming. This is something we call the first principle, and it is somewhat time consuming still. Luckily, someone else has done a load of first principles and sort of worked out a pattern for how to differentiate sort of curves and straight lines and all these sorts of values of x. And I'm just going to move this so you can see the examples over here. And here we can see a load of examples, and then this rule that has been found through various first principle discoveries to find a pattern. So we're going to look at this formula first and then come back to the examples. So we've got our equation of the line here, so y equals to ax to the power of n, and all this is just a is equal to a constant. So for instance, the constant here is 2, constant here would be 1, constant here would be 1, and the constant can be any number. It's just the constant that is multiplying by x. And then n here, all this is just the power, so whatever x is to the power of. So here it's 4, here it's 3, here it's 2, and again this can be any number. It could be 1, it could be a negative value even, it can be 10, something, anything like that. And we're going to then look at the sort of rule that makes that differentiates it and turns it into a gradient, turns it into the derivative. This is here, so it's often called the times and take rule, and all it is we're timesing the constant by our power. So for instance, on the gradient that we've already worked out, you see that we're timesing the 2 by the 1 to get 2 as our new constant. And then our takes part of this is just that we're taking 1 from our power. So for instance here, our power was 2, we're taking away 1, and our power is now 1, and x to the power of 1 is just x. And you can also see this with examples. So we're taking our n value here of 3 and our a value here of 2, timesing them together, so times to get 6. And then we're going to take 1 away from our power here to get 2. Okay, so it's just 6x squared is the gradient of 2x to the power of 3. And again with x to the power of 4, similar thing. You're just taking the constant, the power which is 4, timesing it by the constant which is a to get our new constant 4. And again, take away 1 from the power to get our new power 3. And that's all the times and take rule is. It's essentially just the pattern found through the first principle rule to sort of give you this easier method to differentiate your equations of the line to get nice easy gradients. And this can even be done for sort of that earlier example of a straight line we had. So when we had y equals x plus 1, the constant when it's differentiated in this method just gets sort of eradicated, turns into a 0, and our x value being to the power of 1 and having a 1 constant, 1 times 1 is 1, then x to the power of 1 minus 1, so this 1 minus 1 is then 0, and x to the power of 0 is just 1, so we end up with y equals 1, and so our gradient here is 1, as we discovered earlier. So this can be used for these straight lines, it can be used for these curves, and it can be used sort of any x value to the power of something. that's sort of our rule for differentiation. So thank you for listening. Next time we'll sort of go over some more complicated rules like our rules for sine waves. But yeah, this is the rule for differentiation for these sort of x lines.